out there? Everybody settled in with your quantum popcorn and your jujubes, ready to go? Okay, it is a pleasure to welcome you tonight to Einstein's Quantum Riddle, which is going to be a multimedia, multi-part extravaganza. And it occurs, did I say who I am? I am Brian Keating. I'm so reluctant to talk about myself. I am Brian Keating, a professor of physics at UC San Diego, and I am the co-associate director of the Arthur C. Clarke Center for Human Imagination, the center with the longest name of any center on campus. But that's for good reason. Yes, thank you very much for choosing the name. The center tonight is very proud to present a discussion, a screening, and a wonderful extravaganza, which I should point out is occurring just 10 days before the 100-and-somethingth birthday of Albert Einstein, a picture of whom appears up there when he was a younger gentleman and proposing some of the wild, wacky ideas that we're going to talk about tonight and see in this wonderful Nova special. So I want to welcome you tonight on behalf of the Arthur C. Clarke Center and remind you that we run a series of events here at the Arthur C. Clarke Center, including events like this, but also workshops for writers, for authors, for the public to interact with artists, scientists, and the like. And tonight is going to be, really red meat evening for geeks out there. So I'm really excited about it tonight. So the way the evening's going to go, I'm going to talk for the next 27 minutes. No, I'm going to talk for a couple minutes. I'm going to introduce one of the stars of tonight's program, Dr. Andrew Freeman, who's a research scientist who works with me at the Center for Astrophysics and Space Sciences, close second to the Arthur C. Clarke Center. And he's going to present some initial slides and discussion to sort of whet your appetite for the Nova special that he appears in along with Dr. Jason Gallicchio, who is a professor at Harvey Mudd College. And now I want to give them their formal introduction. So Andrew Freeman is Assistant Research Scientist, UCSD's Center for Astrophysics and Space Sciences, and he is an affiliate of our Arthur C. Clarke Center. He's an astronomer, a cosmologist, and he leverages new techniques and advanced theories to learn more about the universe from the smallest scales, the quantum realm, all the way up to the grandest, most extravagant scales, namely the entire universe. He was an undergraduate at UC Berkeley up north, and he was he was a graduate student at Harvard University and then a postdoctoral fellow at the Massachusetts Institute of Technology, and he joined our group here in San Diego in 2017. After many years working together, we finally got him to be a permanent employee of this fine institution. His friend and colleague Jason Gallicchio is over there, and you'll meet him and you'll see a lot of him in the video tonight, which is appropriate because he is our official representative from Hollywood, California. He is an assistant professor of physics at Harvey Mudd College. He focuses on experimental cosmology and quantum optics. He did undergraduate degrees in electrical and computer engineering from University of Illinois Urbana-Champaign. He completed his physics PhD at Harvard University, did a postdoctoral fellowship at UC Davis and the University of Chicago before joining Harvey Mudd in 2016. In 2013, he became relatively famous in our small circle of experimental cosmologists when he spent a year of his entire life at the bottom of the world at the Amundsen Scott South Pole Research Station, working on the South Pole telescopes. And last but not least is Dr. David Brin, who will be the third member of the panel tonight. He was trained as a scientist before going on to a successful career as a science fiction author and a winner of many, many awards. And he is currently a scholar in residence at the Arthur C. Clarke Center. He did an undergraduate degree in astronomy from a small technical college in Pasadena, known as Caltech. And then he did his PhD right here at UCSD in applied physics and space science. He's a science fiction writer. As I said, he won many awards, including a Hugo Nebula Award for his Uplift universe novels, including Startide Rising, Uplift War. His standalone novel, The Postman, was the winner of both the Campbell and Locust Science Fiction Awards and turned into a major science fiction movie starring Kevin Costner. So he's also part Hollywood. Several of other novels have gone on to great acclaim. And I just want to say, on behalf of the entire Clarke Center community, what a pleasure it is to have these three distinguished scientists who are also masters of communication. And I think that's very rare, and it's very nice to be able to share with you, the public, the people that pay our salaries and our with your taxes. Thank you very much, and please keep doing so. to support this intellectual center, which we think of a little tiny gem within the jewel of La Jolla. So I welcome you tonight, and now I call up to the stage my good friend and colleague, Dr. Andrew Friedman.
All right, thank you so much, Brian. Can you guys hear me? All right, yeah, it's wonderful to be here. I'd like to thank everyone at the Arthur C. Clarke Center, including Brian, Patrick Coleman, Eric Vire, and the director Sheldon Brown for making this event possible. And a special thanks to the Gordon and Betty Moore Foundation for supporting this event, as well as the NOVA episode itself. I'd also like to thank WGBH Boston for producing the film and for helping with previous NOVA screening events at Harvey Mudd College and MIT. And I'd like to thank several guests from KPBS San Diego, our local PBS station, who are here today. I'd also like to thank not only Brian, but my fellow panelists, Jason Gallicchio and David Brin. Brian and David and I have had the opportunity to do a few public outreach events here at the Clarke Center before, so it's nice to be continuing that tradition. And it's great to bring science fiction writers together with scientists to talk about some of the most mind-blowing stuff in the universe. And Jason plays a starring role in the NOVA documentary, as we'll see. And he and I came up with the idea for this experiment together, and Jason has been with me from the very beginning. So thank you so much, Jason, for everything that you've done. Brian has been extremely supportive of the project from the very early stages. And I just wanted to say to each of you, this couldn't have happened without your help. So thank you guys so much. So as somebody who grew up watching NOVA, it's really just kind of amazing and hard to express how cool it is that they made a TV documentary about our work. And as the flagship science education program at PBS, NOVA has set the standard for so many years. In today's world, public understanding of science is more important than ever. And science is just the best process we have to understand the world and to promote critical thinking and to enable us to make complex decisions in an uncertain world. And I'm certainly biased, but science is just also so incredibly mind-blowing. And it belongs to everybody, not just the people who are lucky enough to do it for a living. So I hope that tonight's event will continue to spread the excitement of what it's like to be involved at some research at the forefront of scientific knowledge. And in these opening remarks, I'm going to take the opportunity to tell a story which is a personal story about what for me has been nothing less than the scientific journey of a lifetime. And I've been able to work with amazing scientists from all around the world on a crazy experiment where we use the entire universe to learn something about quantum mechanics, the theory of nature, on the smallest of scales. And we are specifically interested in the phenomenon of quantum entanglement. And we use astronomical observations of distant galaxies to help us understand this phenomenon. And in this spirit, I'm going to share some stories, some behind-the-scenes things that didn't quite make it into the documentary, including the uphill battle that it took to make this experiment happen, as well as some near disasters where it really seemed like the universe was trying to destroy our experiment before it started. And I'll also try to give some additional background on the main scientific and philosophical issues which are at stake. So one of the most amazing things about being a scientist is when you have an opportunity to work on a project which attracts the attention of the science media. And so these are some of the stories that came out after the publication of our paper last year that is the subject of the documentary. And to put things in context, if you write a scientific paper, it's considered successful if a few dozen people cite it, and maybe if a few hundred people read it. But by contrast, when the science media gets involved, you can actually communicate your ideas to thousands, hundreds of thousands, sometimes even millions of people. And so my friend and colleague, David Kaiser from MIT, who also features heavily in the documentary, told us that this episode, Einstein's Quantum Riddle, earned a 1.8 national household rating, which actually beat out the Big Bang Theory for that week, which is pretty cool. And it reached a whopping 3.5 million viewers. And so that's the leverage that you get when you're able to communicate in these platforms is just so much greater than what we scientists get to do in our normal sort of career. So we're just so incredibly excited to get to share the story with so many people, including all of you here today. So to put the story in a larger context, quantum theory is our best fundamental theory of the subatomic world. It's been with us for nearly 100 years, and it's been extremely well tested experimentally. By some estimates, 30 to 40% of the GDP of the world is based on quantum-enabled technology. So you're talking about transistors, lasers like this laser pointer, semiconductors, digital displays, so basically all computers, TVs, laptops, smartphones, communication satellites. I mean, the list goes on and on. And in addition, as the documentary will go into more detail about, there are several emerging technological applications in encryption and computation that fundamentally rely on quantum entanglement. So despite the esoteric nature of the subject, it's actually a very practical subject today. But unfortunately, even though quantum mechanics has been around for nearly a century, experts still disagree about what the theory actually means about the world, about the true nature of reality. In other words, there's no consensus interpretation of quantum theory. And one of the most tricky issues involves the nature and meaning of quantum entanglement. So what is entanglement? Essentially, it's a phenomenon where you have pairs of particles that maintain a special connection no matter how far apart they are from each other and no matter how long ago they became entangled. And as soon as you measure some property of one particle in the entangled particle pair, you instantly know something about a future measurement outcome on its partner. And this is true, even though on either side, the measurement outcomes can appear to be completely random. So Einstein himself didn't like quantum entanglement and didn't like quantum mechanics, and he dismissed the phenomenon as so-called spooky action at a distance, since it seemed to violate his theory of special relativity, which held that no information can travel faster than the speed of light. And while we now know that you can't actually use entanglement to transmit information faster than light, sadly, it's still true that the phenomenon of entanglement is something that we admittedly don't know how to tell a convincing story about that tells us what's really going on. And Einstein hoped that eventually some other fundamental theory, more fundamental than quantum mechanics, would eventually come around to explain entanglement. So in his skepticism towards quantum theory, Einstein advocated a worldview which has come to be called local realism. And for many years, his worldview seemed to be primarily a philosophical one, disconnected from any real-world experiments or tests. But in the 1960s, John Bell, a famous physicist, took some of Einstein's ideas, formalized them mathematically, and actually came up with a way to do an experiment which could distinguish between quantum mechanics and these alternative models that Einstein so wanted to be true. So this theoretical result, called Bell's inequality, it's derived from starting point of several extremely reasonable sounding assumptions about the world. So one of them is realism, and this is just the idea that the real world exists independent of our observations, and objects have definitive properties whether we measure them or not. Bell also assumed locality, which is the idea that if two distant systems are far away from each other, nothing you do to system one can instantly affect system two and vice versa, and this is of course motivated by Einstein's theory of relativity. And lastly, the most subtle assumption that Einstein made implicitly but Bell made explicit, and this is actually the assumption we're most interested in with the experiment that will be the subject of the documentary, is the idea of freedom or freedom of choice. When you measure entangled particles, you're making a choice about how to measure them. And Bell's results assume that this is a perfectly free choice in the sense that it is uncorrelated with any hidden information in the past of the experiment that's missing from quantum theory that could affect the entangled particles. And this turns out to be a rather subtle assumption. But if you put them all together, you get Bell's inequality, which in practice predicts that there should be an upper limit to how often the measurement outcomes could line up in an entangled particle test. So decades of experiments have shown that the upper limit from Bell's inequality is actually violated. We see more correlation between the measurement outcomes than would seem to be possible from these local realistic models that Einstein wanted to be true. And the usual story to explain what's going on is that you've got to give up realism or locality or both. Some of you may have heard that in quantum mechanics, one of the many standard interpretations is that objects don't have definite properties until you observe them. That's what happens when you drop this assumption. People often talk about quantum mechanics being so-called non-local, even though it doesn't actually violate relativity and you can't transmit information faster than light. But what's really definitive about Bell violation in experiments plus Bell's inequality is that the conjunction of all these three assumptions cannot be true in nature. So at least one of them has to be wrong. But there, unfortunately, really isn't any theoretical guidance. They all seem incredibly reasonable. And we're most interested in the possibility of this third assumption. And some of our recent theoretical work has shown that if you keep realism in locality, but you slightly relax freedom, which means that the choices that are made in an experiment, you don't have as many options as you thought you did, it would be possible still for a non-quantum theory to explain entanglement. But ultimately, our experiment is designed to put some tension on this third assumption about freedom of choice. So why do these things matter? Well, from a fundamental physics standpoint, we want to know about the fundamental nature of reality. We want to know, does the moon exist when we're not looking at it? We want to know, is there a hidden influence traveling faster than light and what's going on there? And we want to know, are our choices actually free in experiments? Is there a deeper theory under the hood of quantum mechanics, like Einstein wanted to be true, that could explain entanglement in a way that makes more sense? But independent of this, there's lots of practical reasons why we're also interested in this, and the documentary will go into this a little bit more. There are major emerging technologies that are based on quantum entanglement, including computation technologies and encryption technologies, and every three-letter agency in the world, every national government, major corporation has a stake in whether or not these technologies will work. Quantum encryption in particular is poised to replace the classical encryption schemes that protect all of our online bank transactions today. And physicists think that the quantum encryption should be perfectly secure, but if it turns out that there's a deeper theory under the hood of quantum mechanics, then it might be possible in principle to break these quantum encryption schemes. So there's a lot of practical reasons for being interested in this, these seemingly esoteric ideas. So in an abstract picture of an entanglement test, you have a central source of entangled particles which sends out particles to two distant detectors. Typically, we talk about Alice and Bob on either side of the experiment as experimenters. They choose some measurement settings. So for example, let's say that the entangled particles are photons, particles of light, that are entangled with respect to their polarization. The measurements you make might be very, very similar to, you can see these polarized sunglasses here. If I choose to rotate them at a certain angle, I'm actually asking a certain question of the particle on either side. So these are the kinds of experimental choices that we're actually talking about, where we rotate a polarizing filter that's very similar to these polarized sunglasses. And the photon will either go through the filter, or it'll get absorbed in the filter. A camera behind it records what's going on, and that's what the measurement outcome is. It either goes through or it doesn't. And when we do these experiments, we see more correlation between the measurement outcomes than would be allowed in these local realistic models that Einstein wanted to be true. But what we're concerned with in our experiment is this question of these little choices of measurements. Things like the choices of the angle of the polarizing filter. Are these really free choices? Is there any information in the past that could, in principle, allow us to predict better than chance what these choices would be? So how do you actually choose measurement settings in an entanglement test? Well, in the simplest case, you could let people make the choices. State-of-the-art tests up until recently use things that are called quantum random number generators. But these are devices that are located on Earth. And it's possible in principle that events milliseconds beforehand could have causally influenced one or both of these experimental devices. So based on causality alone, we can't actually know for sure that the purportedly random numbers that are being spit out by these devices are truly random and not influenced by earlier events that become correlated with them. So maybe in principle there's information in the past that could allow you to predict better than chance what the next random number would be. So how do we get around this? Well, our first so-called cosmic Bell test in 2017 outsourced these choices to the universe and pointed telescopes up at stars in our own galaxy and used the starlight, the color of the starlight, like a random number generator to make these choices. Now what this does is that it tells you that wherever the choice was made, it was made far away in space and time. So we did this experiment. We saw a violation of Bell's limit, more correlation than would be expected in these alternative models. And we can't rule out entirely that they're responsible for entanglement, but what we can say is that it had to have happened far in the past. So the nearest star was 600 light years away, in this experiment in particular. So an alternative theory would have had to have set things in motion 600 years ago. And this was a dramatic improvement over previous tests where the limit was only a few milliseconds before the experiment. And in 2018, and this is the subject of the documentary, we went even further. Instead of using stars in our own galaxy, we used distant galaxies entirely, these bright galaxies called quasars, which emitted their light not hundreds or thousands of years ago, but billions of years ago. So this is what our cosmic bell experiment in the Canary Islands actually looked like. So in January 2018, we sent polarized entangled photons through the open air to these detectors that were located near these two big telescopes that were separated by about 1 kilometer. And for the first time, while the entangled particles were in flight, we waited for a fresh random bit of information based on the color of the light from each quasar to choose how to measure the entangled particles, all while they were still in flight. And we needed to do this very rapidly to make sure that no hidden information could go from one side of the experiment to another in order to mimic and fake quantum entanglement using some other theory. And by outsourcing the choices to the universe, again, we can't totally rule out alternative explanations distinct from quantum mechanics from explaining entanglement, but we can push them into a very, very far corner in the past. In this case, we can push things back billions of years ago, almost all the way back to the beginning of the universe. So, switching gears a little bit to provide some backstory, before I came to UCSD in 2017, over the past 6 years or so, to design and implement our experiment, we built a unique collaboration at UCSD, MIT, Harvey Mudd, University of Vienna, and elsewhere. So this is a good opportunity to tell some behind-the-scenes stories from my perspective of how this project came into being. So my own personal involvement with the project began just over 6.5 years ago at John Harvard's Brew Pub in Cambridge, Massachusetts. And at that time, I was a postdoc at MIT, and Jason Gallicchio was in town visiting from his postdoc at the University of Chicago. And we had both gone to grad school at Harvard, so John Harvard's was a very familiar place where many burgers and appetizers have gone missing over the years. And it was the night of my wife's bachelorette party. And while she was out with friends, Jason and I were talking physics over dinner and beverages. And the idea of quantum entanglement tests came up. And Jason talked about his idea of using the oldest light in the universe, the so-called cosmic microwave background radiation, to make experimental choices in an entanglement test. And this sounded pretty cool as a thought experiment. But since my background was in infrared and optical astronomy, I naturally wondered if there might be other astronomical sources that would suit our purposes better and might be a little easier to work with. And these included things like exploding stars called supernovae and bright distant galaxies called quasars. And these are things that are bright enough to be seen halfway or all the way across the universe. And eventually I became convinced that quasars were the best choice, and I was able to convince Jason too. And after this conversation, I began thinking about how far apart the quasars had to be from each other and how far away they had to be from us in order for them to serve the purposes we had in mind in the experiment. And so these are some notes with some of the theoretical calculations that were relevant that this conversation set in motion. So as the idea that Jason and I discussed began to look more and more promising, I brought the idea to David Kaiser, my postdoctoral mentor at MIT, who was thankfully incredibly supportive and enthusiastic. And as early career scientists, Jason and I knew that there was just no way that we would ever be able to do this experiment on our own without help from people like Dave. And Dave and I soon began discussing this idea with Alan Guth, another eminent theoretical physicist at MIT. And as soon as Alan became interested and was on board, I began to think cautiously, maybe this might actually happen. But, amongst us, Jason is an honest-to-goodness experimental physicist, but Dave and Alan and I are astronomers and theoretical cosmologists, so we're not people who work with experimental hardware, admittedly. So, and we also know that we needed a partner who really had the required experimental expertise in foundational quantum experiments, as well as the funding and infrastructure, and the sway to actually convince an observatory to let us do this crazy thing with these huge telescopes. And as it happened, Professor Anton Zeilinger was from the University of Vienna was visiting MIT in October 2013 to give the physics colloquium. And he leads arguably one of the world's top experimental quantum optics groups. And his team has already performed a number of experiments, including entanglement tests in the Canary Islands. And realizing this unique opportunity, Dave and I signed up to talk with him afterwards, and we cornered him with our experimental proposal. And to our delight, he was not only incredibly enthusiastic, he told us he'd actually come up with the same idea independently years ago, and he was just waiting for the right time to actually do the experiment. So by that time, Dave and Jason and I and Alan had already solved some of the theoretical cosmology problems needed to choose the right astronomical sources in the experiment. And we'd started to convince ourselves that it was going to be feasible with present technology. And so it turned out to be the perfect marriage, since each of our groups had the expertise that the other lacked and needed. But a huge piece was missing. So this was, of course, funding for the US side of the collaboration. And over the next couple of years, we applied for grants to support the project over and over, and kept hearing no after no after no. And every time we submitted it to some program, we kept hearing things like, well, this is interesting, but you really should be submitting it to this other agency. And unfortunately, that's what you get in this very, very tight funding climate when your project doesn't fit into a neat box. And our project involved a unique combination of observational astronomy, theoretical cosmology, experimental quantum optics, and even aspects of the philosophy of science. So we ended up being penalized for trying to do something unique and interesting across several disciplines. And it was very, very frustrating, especially since Anton and his group were ready to go, and they thought it was really worth doing. And in the meantime, I've been visiting UC San Diego over several years, and around 2013-14, I began to discuss this project with Brian Keating, who himself is one of the world's leading experimental cosmologists. And I was overjoyed when Brian actually thought the project sounded exciting and interesting. And we are so happy he agreed to join our latest funding proposal at the time to get funding from the National Science Foundation. And thankfully, after so much frustration, we found out in May 2015 that the NSF had funded our project. And as such, Brian's support from the very early stages had a huge, huge role in the eventual success of this experiment. And this funding allowed me to work at MIT and then also to work on this project at UCSD, and where I eventually was able to come here a couple of years ago with Brian's help. And I've been able to work with a number of amazing students, including one of Brian's graduate students, David Leon, who helped with some of the key theoretical cosmology calculations for the project. So in the end, with NSF funding for the US group and European funding from Anton's group for the experimental hardware and the manpower, we were finally in business. And thinking back, it's pretty amazing that the thought experiment that Jason and I envisioned actually happened in the real world. And from idea to completion, it took just over 6 years, which is actually pretty fast in science. And I think it's safe to say that the experiment succeeded beyond our wildest dreams. And I just want to give, again, a special thanks to Jason for being with me from the very beginning on this project. And you'll get to see a lot of Jason in the documentary. So to go back almost to the beginning of the universe, we ultimately chose quasars because they're the brightest known astronomical objects at their distance. And at least on human timescales, they're always on. So they're bright, and their brightness and color can be used as a ready source of random numbers that were generated a long time ago in a galaxy far, far away. And we could use them to tell us how to measure our entangled particles. This is exactly what we needed for our cosmic bell test. But these quasars are really faint objects, so we needed fairly large optical telescopes to observe them from Earth. And this is where we really needed a place like the Canary Islands, which had exactly the right geography and astronomical resources. And we got an amazing amount of support from people at the Roque de los Muchachos Observatory on the island of La Palma. Thankfully, Anton and his group had already worked with this observatory on previous experiments, and we were able to somehow convince the director to give us discretionary time to do this crazy thing. So here are some pretty amazing panoramas of the experimental sites in La Palma taken by Jason. And here's a bird's eye view from Google Earth showing the 4.2 meter William Herschel telescope and the 3.6 meter Telescope Nacional Galileo. The entangled particle source was sitting on a landing pad in front of the Nordic Optical Telescope in a little container, which I'll talk more about. But you can see that it's right in the middle because we needed line of sight between all three sites. And we really needed such big telescopes to get enough light from these really, really faint distant quasars in the limited time we had on the telescopes. So since I was working on the design, theory, software, and data analysis for the experiment, my role in the experiment was remote, so sadly I didn't actually get to go to the Canary Islands. So this is why in the documentary my name gets mentioned very, very briefly, and I think if you look really closely, you'll see about a quarter of my head on Jason's laptop on a video chat. And we nominally had 3 nights on the telescopes, 2-hour blocks in January of 2018, and I was in charge, along with Jason, of selecting which pairs of quasars we'd actually observe. So since everyone was relying on us, we didn't want one of our laptops crashing to mean the end of the experiment, so we hedged our bets with Jason going to La Palma and me staying in San Diego, where I had access to other computational resources and several backup computers. And over several years, we'd each written parallel versions of software which would select the optimal pairs of quasars to observe with these 2 telescopes at any given time from a huge database, which started out at about 1.5 million objects, but we eventually cut that down to about 60,000 of the best candidates. But ultimately, due to weather and other challenges, it was impossible to know exactly when the experiment would start. So, of course, we ran many scenarios in advance, but when push came to shove, our software had to be able to tell us in real time the most distant pairs of quasars we could actually observe at the same time with these telescopes. And this is a weird thing, and we had to write our own software because nobody in astronomy wants to do the kind of thing that we did for any sane reasons other than what we did. So the brighter the quasars were, the faster we would get our experimental data. But since the quasars themselves vary in brightness, and we didn't really know in advance if we'd need 10 minutes or several hours of data. And it would be cutting it really, really close if it went beyond our allotted time. The best we could do was build into our software our best estimates for how long it would take to get the data we needed. And I'll leave the story of what actually happened to the documentary, but keep in mind that while we're doing this high-stakes science, there's this documentary film crew with boom mics and cameras hovering over everyone in the Canary Islands. And we're all extremely honored to have the NOVA crew there to tell the story of our experiment, but it really does add to the pressure when things are going wrong and you're trying to solve problems on the fly, and then there are camera crews looking over your shoulder. So it's definitely an interesting experience to be part of. So speaking of things going wrong, I'm going to tell a story that didn't quite make it into the documentary, but looking back, there was a near disaster that almost destroyed our experiment, and it could have been even worse. So keep in mind, it's a huge logistical challenge to get the experimental hardware that was built in Vienna to the Canary Islands. So for example, here's a shipping container that actually served as an office. It's got an air conditioner and windows, and this is where the entangled particle source lived. It's sitting on the landing pad in front of the Nordic Optical Telescope, and there's a couple of windows. The entangled particles are generated, and they're sent through the open air out through these windows to the 2 other experimental sites. But keep in mind that this observatory is 2,300 meters plus above sea level, and unfortunately, a couple of weeks before we had time on the telescopes, there was a huge storm, and the winds got up to 70 to 80 miles per hour. So keep in mind that this is where the container is supposed to be. This is where it ended up. So it literally went end over end, and 2 hours before this, a couple of people were working inside of it. They could have been killed. Thankfully, no one was hurt. And thankfully, in addition to that, if it had been a couple meters to the left, it could have gone over the railing, gone over the mountain, and landed in the ocean. And if that had happened, I would have thought, maybe the universe doesn't want us to do this experiment. So, the windows of the office didn't fare too well. And even worse, the most sensitive part of the experiment, the entangled particle source, which is a special crystal, you shine a laser into it, and it shoots out 2 entangled photons, that was just destroyed in this accident. So our collaborators in Vienna were heroic in their efforts to cobble together a replacement in less than a couple of weeks from what they could get a hold of. And this type of equipment is not something you can just go pick up at Walmart. So they really had to make it work. And ultimately, heavy equipment had to be brought in to right the container. It had to be weighed down with these cinder blocks to make sure that the disaster didn't happen again. And here I really want to single out Dominik Rauch, a PhD student in the Zeilinger group in Vienna. He's the lead author of our paper and a key star of the documentary, and he should get an amazing amount of credit for leading the experimentalists on the ground in La Palma, in both coordinating our response to this disaster, and really making sure that the experiment actually worked when we had time on the telescopes. And ultimately, we couldn't have done this at all without the support of folks like Chris Ben at the observatory, and of course, Anton and his entire group from Vienna, along with all the other undergrads, grad students, postdocs, and researchers in the entire collaboration. Science today is really a huge team effort. So although Jason and I came up with this idea, there's no way that it could have happened without a huge amount of help and support from people like Brian and people like David Leon and people too many to mention. And ultimately, we're just amazing that they made a documentary about it. So now I'd like to invite you to enjoy the story of Einstein's quantum riddle. It's just under an hour, and after that, our panel, including myself and Jason, David Brin, and Brian, will be happy to take questions from the audience. So thank you so much.
Hello.
So, any questions? No, I'm just kidding. That was phenomenal, of course. I'm going to ask some...
Under your seat, you will find the first page of your exam.
That's right. So that was really delightful. I am going to ask for audience questions in a few minutes. I'm going to kick off with a couple of questions of my own and discussion amongst the panelists and stars. I think several stars were born tonight, these two gentlemen to my immediate left. We have to leave this auditorium or we will all be collapsed in about 20 minutes. So we will do some, make a strong effort to remain on time. So first of all, that was an awesome documentary. They do such phenomenal work with NOVA, and it's really a testament to the work that you guys put in for the better part of a decade. So thank you for that. What I want to start off with first is really kind of the grand arc of the story as a personal story, as a human story. We get so caught up with all the mesmerizing science, as scientists especially. What is it like to actually participate in these kinds of discoveries? What does it feel like to understand something? It's one thing to understand something, and it feels so good when you actually do understand something. I've had that experience once or twice in my life. But to understand something for the first time in human history, that's a phenomenal accomplishment. What did that feel like for the two of you guys?
I think it's really hard to put in perspective just how amazing it is to think back to thinking about this idea, basically like drawing it on a napkin, a thought experiment, and to actually see it come to fruition, and to actually see the experiment successfully produce results in a way that we can interpret. It's sort of indescribable how awesome it is to know that you're part of the scientific story that stretched back many generations, and and that I can't speak for Jason, but I'm not Einstein, but it's just amazing to be following in footsteps of people like that.
It's too bad for him to be wrong again after the cosmological constant, which he called his greatest blunder, and now this. The guy could have had a good career. Jason, what was it like for you?
It was great. So we discussed this, we wrote a paper, and it we were going around giving talks, and people were like, oh, that's kind of cute, and I was a little bit worried that this wasn't going to go anywhere, and I went to Vienna for it was a 50th anniversary of Bell's Inequality. Bell's Inequality was a conference, and I was sort of too late to really participate in the actual conference part, but Anton Zeilinger, the guy from Vienna, invited me to give a talk to his group after. And normally you give a seminar and everyone sort of nods along and there's one or two questions at the end. And this time I could tell there were questions the whole time, and afterwards people were just pounding me with questions for 2 hours, and everyone was super excited about this. And I finally thought, I think this might actually happen. That was just a great feeling that day.
And from a perspective, I was mentioning before before we met earlier today, speaking in conversation, I was watching a movie, a very technical documentary called Ant-Man and the Wasp, on an international flight recently. And, at a certain point early in the movie, they go, we have to go into the quantum world, the realm of the quantum with entanglement. And they really kind of throw all these buzzwords together. And it's clear to me that they understand it, at least as poorly as many physicists do. But I want to ask David something. What is it about the quantum world, the quantum realm, that so fascinates you and those of your refined ilk, the science fiction community? Why is it so fascinating to non-specialists? Very arcane branch of mathematical physics, after all.
Well, I do have to emphasize that even though I got my doctorate about 200 meters from here, and I am a member of the priesthood, I have my union card as a physicist. I'm more of a Franciscan. These are the Jesuits here, working in the airy-fairy realm beyond. Is that Freeman and Ime? Yes, we have one of the greats out there, Freeman Dyson, who's migrating gradually in a quantum sense with his wife to a better climate here from the Institute for Advanced Study, which is featured in this show. And he was on this stage here just a few weeks ago. So speaking as a barefoot Franciscan, I have to tell you that the notions of what the world can look like from the point of view of communicating to, this wonderful civilization, is the thing that strikes me is shows like Nova. No priesthood in the past that interpreted what the world was about and what God's words were, if you believe, no priesthood was ever so eager to share. So eager that whatever degree that the scientists plus good storytellers could possibly achieve to communicate what your tax dollars paid for, you are part of this adventure. You aren't kept outside. You're welcome to come in. And I invite all of you to find out when the seminars are held here on campus. You can come and eat your lunch in the back of the room. They won't like it if you sit in front with the Nobel Prize winners till the third or fourth time. But other than that, come and eat your lunch.
So along with the concept of the microscopic universe that's explored here, you guys also played out a role on the grandest cosmic stage itself, which is the vast bulk of the cosmos. And to think about connecting the smallest quantum objects with the entire cosmos is really a phenomenal result. And a lot of times these two things emerge and are synchronized, again, in concepts from science fiction, things like wormholes and extra dimensions and even the multiverse. I know you guys have thought about this, so what are some of your thoughts about this and why it resonates so deeply with our curiosity?
So when you're thinking about entanglement and you're thinking about something that seems like it's very far away, somehow affecting something, even farther away, one of the things that people have speculated about in science fiction, which has now kind of actually become a reputable subject in physics, is the idea that perhaps the idea of wormholes, which comes up in Einstein's theory of general relativity, the idea that there's shortcuts between different places in space and time. Some people are taking seriously the idea that entangled particles might actually be described by a sort of quantum scale wormhole. And toward the end of the Nova episode, people were talking about speculative ideas where you can actually think about entanglement itself as being sort of the fundamental ingredient of nature in a new theory of physics. There's a certain sense in which entanglement is more fundamental than quantum mechanics. It's really just this question of, if you have two places in space and time, two particles, are they independent of each other or not? And in classical physics, it's possible for those things to be independent of each other, but in quantum physics and perhaps in a new physical theory which combines quantum theory and Einstein's theory of gravity, maybe it's just not possible for two places to really be independent of one another. And maybe there is a picture in which space and time are emergent concepts, and you could actually envision a network of quantum wormholes between all these entangled particles. If you were able to go down into the level of where Ant-Man was, and I've been there, and it looks exactly like that. Then maybe you would see these connections between things that naively look like they're really, really far away from each other, but maybe in this new physical theory, if they're connected in this way, they're actually really, really close together.
Mm-hmm. I just want to point out, thinking about this and thinking back to when I met I met Andy actually through the origin of this. The origin story itself actually relies on a series of networked and interconnected and correlated events, but it all began with your mother, who's in the front row, who I met about 7 years ago. And I think it's interesting to think about these origin stories, and if one thing had changed, a slight difference, maybe we wouldn't be here tonight, maybe we would, but I think it's important to acknowledge how these things come together in most magical ways.
Yeah, and interestingly, speaking of entanglement, my parents at one point met David Brin randomly on an airplane, and they my dad had read his books, and so it is pretty amazing, and that when you come to think of it, when you meet anybody in life, Jason and I met in graduate school. Think about all the things that had to happen for that to be possible. Yeah. It's pretty mind-blowing.
Oh, and in the Clarke Center archives, you might find two. Did we do two together or three? We did the three physicists, and nobody asked us which one was the tenor or to sing. But
Thank God.
We did one on multiverse, and what were the other two?
We talked about the physics of free will.
Yeah.
And then the mind of God.
Oh,
yes.
yes.
A very, very
Yes.
simple subject.
Yes.
Which brings me to my next and maybe final question, depending on how many questions you all have out there. So at the end, Anton Zeilinger, one of the leaders of this branch of research, he starts talking about what Einstein thought about. The one question that Einstein wanted to understand was what was going on in the mind of God. And I wonder, I don't know your particular views on that particular subject, but if you could ask Einstein or tell Einstein something after all your peripatetic wanderings in space-time, what would it be? What would you most want to tell the great maestro of physics, Albert Einstein? Jason, start with you.
No, I think I would have liked to explain Bell's inequalities and ask, just start a discussion about, when he was thinking about all these things, it was mostly a philosophical matter of whether there was some underlying reality or whether the Bohr-Schrödinger description was right. And it wasn't until after he had died that people realized that this is not just a philosophical issue, but something that was experimentally testable, and the experiments came out in a certain way. So, I would sort of like to present him with the theoretical and experimental evidence and say, all right, now what?
David?
Yeah, I was told by my father, and I never really confirmed it, but I was told by my father that I saw Einstein play the violin when I was 3. And the stories must have been traumatic because actually it's a weird thing that I've never told anybody about myself, and that is that I couldn't look at a picture of Albert Einstein until I was 12. It creeped me out.
Spooky. It was spooky.
It was spooky. But other than that, I would say, I'm not going to waste any time pitying Albert Einstein for getting a couple of things wrong. The theological issues are another matter. It's very clear that we can chase down God, whether he's there or not. One of the things that Zeilinger was talking about was it was Kaiser, carving away what's left. And I dispute with a lot of my atheist friends. I say, no, all you've done is chased him out of 99% of the possible. He's still giggling, the God of the gaps. Whether he's there or not, you can still hear the giggle.
No, famously, he said, God does not play dice with the universe, and he used to speak quite reverently about it, and yet we have great evidence that he was probably an atheist in some ways. Andy, what would you most want to tell Einstein, and if you could somehow communicate, maybe you can, beyond the realm of the current...
Well, it's interesting because he's so mythologized in our culture. Whenever the idea of Einstein being wrong comes up, people get really excited and interested, and that I would say that Einstein, to the extent that he was wrong in some of the most interesting ways in the history of physics. And although the documentary kind of tied it up in a nice little bow, I would say that the questions that Einstein raised that lead to the idea that there are possible loopholes in these experiments, they have not, in my opinion, all been definitively addressed. And that's why we need to do experiments like the one we did, and there need to be future experiments to keep pushing things further and further.
Absolutely.
And so, I would want to talk to him about, just as Jason would, I would like to see his reaction to the state of the art of knowledge today, and then also, I would love to ask him, okay, what do you think we should do next?
Well, he also famously said, imagination is more important than knowledge, and we're here in the Arthur C. Clarke Center for Human Imagination. So I want to take questions from the audience, and we have some microphones, I believe, somewhere. There's one over here, and there's one probably over there, if symmetry holds. So make your way to the microphone so you can be recorded and publicized and encrypted by those Chinese scientists that we saw. And I will start. We have a good turnout. Good. So I'll begin over here, and then we'll just alternate for the remaining 15 minutes or so. Yes, please,
Okay,
sir.
gentlemen. 2 quick questions. One is, has anyone been able to repeat your experiments and get the same results? And 2, are there any Nobel implications for this particular work in physics?
No.
I would say that we're not going to win a Nobel Prize for this because most of the people in the physics community probably expected us to find results that are consistent with quantum mechanics, and we certainly did too. A Nobel Prize would have only been a result if we found something that was completely unexpected that was then confirmed by others. And as far as whether or not our current results have been confirmed by others, so far we're the only group to do an experiment with quasars, but our competitors and / collaborators, including Zhangwei Pan's group in China, they've also done another cosmic bell test where they used stars in our own galaxy, similar to what we did in our first cosmic bell test, and all those results are consistent with quantum mechanics being correct. But so far, no one else has done a cosmic bell test with quasars, but we hope somebody does.
A quick question for you two guys. Now, those two quasars, the oldest one is 8 billion years old, is that?
The oldest one was a shade over 12 billion years.
12 billion years. Okay, so they were chosen in opposite directions. So at what point after the Big Bang were they causally in reach of each other? Was it before or after the 380,000 years?
So the universe is about 13.8 billion years old. And
They've all watched Big Bang Theory and they can sing the song.
Fair enough. And if you look at the furthest place in time where something could have jointly influenced both of the quasars, that was a shade over 13 billion years ago. So it wasn't all the way back.
It wasn't all the way back.
It wasn't all the way back. And we would love to do a future experiment where we use even more distant, fainter quasars. But we would have needed bigger telescopes and more time in order to make that happen.
Yes, and another camera crew to get Andy on film more often. Yes, sir.
This is the second time that I've seen this. I saw it on TV when it came out, and I was interested in seeing it again. The thing that I sort of came away with was if you influence one entangled particle instantaneously, you influence the other, which immediately brought to mind that was instantaneous, like faster than the speed of light, which Dr. Freeman said twice during his introduction, you can't transmit information faster than the speed of light. This seems to contradict that. Unless those two particles actually exist at the same place in the same time and you're influencing the same particle.
So it's a little subtle. Something seems to be happening faster than the speed of light, but it's really the establishment of these correlations that's happening. You can't use this to communicate because any one person sees a completely random result no matter what the other person does to the other particle. So in order to tell that the correlations between them were established in this interesting way, after they do their measurements, they then just have to communicate normally and compare results. And that always has to happen at or below the speed of light. So there's nothing that somebody on one side can do to their particle to influence what's going to happen to the other particle. It's always going to look random to both people.
Yeah,
So it's sort of, it's a weird in-between land between, what exactly is happening faster than light is a little bit subtle.
Einstein is still reigns supreme when it comes to actually telling somebody at a distance something that they would like to, information they'd like to have. So if you do this experiment and you have it be a light year apart, the correlation is going to be instantaneous if action at a distance works. But neither person is going to know this until light has transmitted information for a year.
Yeah, it seems to violate the spirit of Einstein's theory of relativity, but it doesn't actually violate the letter of relativity. And the thing that we can say for sure is that if Brian measures 1/2 of the entangled particle pair, then he instantly knows something about what Jason would measure in the future. And so we now don't think that anything Brian does to make the measurement instantaneously changes the state of Jason's particle in a way that is instantaneous. You have to do the checking later, and that happens at slower than the speed of light.
The one possible use is that some kind of military or commercial decision. If you make it here, your associate 1 light year away may know something about what you decided. But that's kind of iffy.
Okay, we only have 5 minutes left, so I want to go back over here. Is there a question? Yes, young man.
So in terms of you talked about earlier about wormholes and the implications that it could have, but do you think that your results could provide evidence for something like string theory, which has compactified dimensions, so you could potentially see results that look like entanglement but are actually not traveling faster than the speed of light?
I think that our experiment, unfortunately, is not powerful enough to test something like string theory, which is a candidate for a possible way of taking quantum mechanics and general relativity together and merging them into a coherent whole that agrees with each other. But I do think that future experiments that involve cosmology, that involve using the universe as a laboratory, are probably our best bet for gaining experimental evidence for these new theories. It's becoming harder and harder to build particle accelerators that reach the energy scales that are necessary. So I would say that our experiment is definitely in the spirit of trying to learn about these new physical theories. Eventually we want to find a new physical theory that makes predictions that are slightly different than quantum mechanics, where we can understand what the new physics has to be in order to explain that.
Okay, now we come to the lightning round because we only have a few minutes left before we engage in our black hole brownies and quantum cookies. So we'll go over there.
Sure thing.
Quickly, please.
So I also am absolutely fascinated by quantum phenomena. One phenomenon I find really interesting is something that the Pear Lab at Princeton has looked into in the past, which regards our ability to influence random number generators. And I was wondering if you guys happen to have any input on that regarding what maybe stuff that you've heard about in this working in this field or not.
Well, an interesting question is, how good are humans at producing random numbers, for example?
Pretty bad. Pretty bad.
Pretty bad is the answer, yes. Yes, I absolutely agree. And it's certainly an interesting idea to, instead of letting quasars make the experimental choices, we could let humans make the choices, but in order to make sure that no influences at the speed of light or slower could affect the results, human reaction time is slow, and so you'd probably need to have one person on the Earth and one person on the Moon in order to make sure that no hidden influences could affect things. It's a separate question, which I think is what you're asking about whether or not the human mind could influence a random number generator.
Correct.
That's external to a human. I would say that if that happened, my mind would be blown. I'm skeptical that's possible. I think it's certainly worth testing the limits of the human mind scientifically in whatever ways are possible. I would be extremely surprised if I could reliably change the outcome of a quantum process that's far away from me.
So we'll take one more question, then we'll adjourn for refreshments outside where you can engage with the scientists and the panelists as well. Yes, sir.
Assuming the Big Bang, why isn't everything already correlated and entangled?
So that's a very good question, and it depends on which model of the Big Bang you look at. So the sort of maybe original model where you just trace back the expansion of the universe that we see today. You just trace it back, trace it back, trace it back, and you ask at any point, so say the light was emitted from this quasar approximately a billion years after the universe was created, and you ask, what could have influenced that? If you really trace back all of the matter in our universe, the matter and light in our universe, it turns out that a quasar on one side of the sky could not have influenced a quasar on the other side of the sky. Even though everything in the Big Bang was an incredibly small space, it expanded so fast that light that left in this direction couldn't catch up to something in this direction because they were expanding away too fast. So it's subtle because you think that in the Big Bang, yeah, everything was all on top of each other. Certainly everything had a lot of time to mix. But the expansion in the beginning was too fast for that to really work out. Now there are problems with this, and people have proposed extensions, and one of the extensions is the theory of cosmic inflation, and that is specifically designed to allow the pasts of these things to interact so that everything could mix.
Thermalization, smoothing
That's
out.
one way of doing it, yeah. And so there's reasons to believe that did happen, and then again it could be that something way back in that period of cosmic inflation affected all of the things that we see. But yeah, that's sort of a.
Mm-hmm. Yeah, I would say that if inflation happened, then the best we can do is to progressively use more and more distant astronomical sources and push this loophole back further and further into the inflationary epoch. But this loophole, that's the best we could ever do if inflation happened. And your question's a valid one. And it would still leave open the possibility that everything was predetermined at the origin of the epoch of inflation, which put the bang into the Big Bang. So that's a possibility that can't be ruled out with the kinds of experiments that we're thinking about.
Okay, well, I do want to thank everybody for coming out on a Monday evening in San Diego and invite you to entangle and mix and mingle with the panelists outside. Thank you all.
Thank you.